This is the official watch, by the way. It's one of those things that beeps at midnight because it's setting itself to the Bureau of Standards. And I'm sorry, that's right. You can tell I was born a long time ago. You too. Okay. Well, welcome to our fifth press conference, the first of Wednesday, at the 225th meeting of the American Astronomical Society. It's a pleasure to see another almost full house. Today's speakers are reporting on one of those objects that's of great interest to astronomers, sort of the archetypal objects that we study, like the Crab Nebula. This one is Eta Carinae in the southern hemisphere. It's one of the superstars in not just a literal sense, but a figurative sense, or vice versa. And we have four speakers from Goddard who have been studying this for a long time, or are associated with Goddard. They actually have other home institutions. Michael Corcoran from USRA and the Goddard Space Flight Center will be talking about the X-ray variability of Eta Carinae. Mairan Teodoro will be talking, who's from Western Michigan University, will be talking about changes in Eta Carinae's physical properties across periastron, which occurred relatively recently. Thomas Madura from NASA Goddard Space Flight Center will be talking about deciphering Eta Carinae's interacting winds with the things you see here, 3D printed models, a revolution perhaps in the way we visualize things in astronomy. And Ted Gull from NASA Goddard Space Flight Center will be talking about the blue-shifted crab of Eta Carinae. As usual, our speakers will each present for 7 minutes, one after another, and we'll hold questions until the end. So mark down any particular questions you have as things go along. We'll take questions from the audience and from the web, and we ask our speakers to use the cursor on the computer here rather than a laser pointer because people will be watching the webcast. So we'll begin with Mike Corcoran.
Thank you, Larry. Let's see if I can
hit the reset button.
Okay, so as Larry said, my name is Mike Corcoran. I'm from the University Space Research Association in NASA Goddard, and we're here to tell you about some goings-on with the superstar Eta Carinae, which is the most luminous and massive star within 10,000 light years. Eta Car is also a binary system, and it has a companion in a very elliptical orbit that passes very close to Eta Carinae itself every 5.5 years, and when this happens, all sorts of interactions take place that you can see throughout the entirety of the electromagnetic spectrum. So I'm going to talk about some of the changes we saw recently in X-ray radiation from the system, and where those X-rays come from, and what they tell us about the system. And then my colleagues will tell you about the changes through ground-based optical observations, Hubble Space Telescope observations, and then we'll try to put this together in a hopefully sophisticated 3D model. Is that me? So why is Eta Car important? One of the reasons is that it's not only the most massive and luminous object that's close to us, but it's also extremely erratic. It's best known for this event here called the Great Eruption, when the star basically exploded and at energies that would destroy a normal star, but Eta Car survived it fine, but it did expel tens of solar masses of material outward, and you can see this material expanding outwards in this in a bipolar nebula, which we call the homunculus at present. So what you see here is a history of the optical light curve from Eta Carinae from 1840 basically through the present day. And you can see the enormity of the eruption, which made the brightest star in the southern hemisphere. The star itself, its image is fairly well known, I think, to everyone, or a lot of people anyway. So this is a famous Hubble image of Eta Car. What you're really seeing here in these big bipolar lobes of the expanding shell of gas called the homunculus. And the star itself is the bright point of light close to the center of the homunculus. So if we could zoom in, we can with the Hubble Space Telescope. You see that even the surrounding areas of Eta Carinae are very complex, and Ted will talk about some of these complexities later on. The star itself is here, this bright dot. And if we could zoom in further, we can't do this telescopically yet, but we can through computer simulations. We'd see something like this. This is basically what the binary star looks like. Both these stars, I should mention, have extreme luminosities. Eta Car is about 5 million times more luminous than the Sun, while the companion, even though it's less luminous than Eta Car, is still emitting about 1 million times more luminosity than our Sun. And as a result of this extreme luminosity, the stars are basically blowing themselves apart. You have an enormous radiation pressure that's driving material off the stellar surfaces in the form of strong stellar winds, and these winds interact to form this bow shock. The winds are quite different, though. For Eta Car, which is down here, this is, put the cursor right here. So here's Eta Car, and here's this material here is the wind, meant to represent the wind of Eta Car. That wind is very dense and relatively slow. It's only moving at 1 million miles an hour. The wind from the companion, on the other hand, is very thin. It's low density, but it's very fast. It's moving at about 6 million miles an hour. So this interaction forms this bow shock around the companion star. Now you can imagine a 6 million mile per hour object smacking in and decelerating to zero quite rapidly. That would generate a lot of energy. And that energy appears in the form of heat. So if you looked at the temperature map of this system, you would see a very, very hot gas right here in yellow, representing gas at tens of millions of degrees. This gas is hot enough and dense enough to generate observable X-rays, and it's these X-rays that we're interested in. Here is a rather recent history of the brightness of Eta Car in X-rays. These are data points taken with the Rossi X-ray Timing Explorer starting in 1996, shortly after the launch of RXTE, and continuing now through the present day using the Swift X-ray telescope, which you see here in blue. And you see that the X-rays characteristically vary. They all exhibit a sort of a gradual rise, a rather abrupt drop to a minimum state, and then some recovery. And it's this drop from the minimum to minimum that defines the period of the system as 5.5 years, and we understand this now to be an orbital period. So what we think is happening is that as the stars approach each other in their elliptical orbits, the X-rays brighten because the winds get more dense, and eventually they reach a maximum state. Where's my pointer? And then drop very rapidly as the X-ray emitting gas moves behind the dense inner wind of Eta Car itself. This happens when the stars are closest approach and the stars are moving most rapidly. So very quickly the companion moves around Eta Car and suddenly reappears. And you see the reappearance of the X-rays. And then the cycle repeats. You note that the cycle does not repeat exactly from orbit to orbit. And this is an interesting measure of the variability of Eta Car. What I'd like to show you now is a brief animation comparing the 4 orbits that we've seen with RXTE and the Swift X-ray telescope. And I'll just point out here, what you're seeing is an X-ray image now of Eta Car taken with Chandra and observed by my friend Kenji Hamaguchi. And what you'll see is that we've timed this, we've sort of simulated the brightness variations to time the brightness of the central source with the light curves that will appear here, to emphasize the flickering and abrupt nature of the decrease in X-rays. So let me see if I can start this. It's worked before, so hopefully it'll work again. So what we'll see now is the 1998 X-ray minimum, data around then, and you can see that it's sort of broad and flat-bottomed. In 2003, we saw something very similar, a broad, flat-bottomed eclipse. In 2009, though, we saw something a bit different. The eclipse was not quite as broad. It recovered more rapidly. And surprisingly, in 2014, the last X-ray minimum in the last periastron passage, the recovery was sort of intermediate between the fast recovery in 2009 and the more leisurely recoveries we've seen previously. And so you can see the flickering of the star, I think, is a nice little representation to emphasize the compactness of the X-ray source. If you zoom in on the X-ray minimum state, and so this compares the 4 X-ray minima in one plot, you can see the changes here in the recovery, and you can see that the start of the minimum happens at almost exactly the same time in all four orbits that we've seen. So that's very stable, but there's something that happens as a star recovers. We understand now that the minimum, this X-ray minimum, is actually composed of two distinct physical causes. One is a deep minimum, we call the deep minimum, which is basically an eclipse or an occultation of the X-ray emitting gas behind the wind of Eta Car. And then something happens to the X-ray emitting bow shock, and it cools very catastrophically by a factor of 10 or so. And we call this state the shallow minimum, where you don't see any X-rays from the bow shock anymore, but you do see sort of an X-ray glow surrounding the companion star. And these we understand this now from data taken with Chandra, XMM, Suzaku, and now NuSTAR by Dr. Kenji Hamaguchi. So let me just wrap up with some conclusions. The X-ray brightness, I didn't really emphasize this, but the X-ray brightness just prior to the X-ray minimum closest approach has been increasing over the last few years. And in fact, in July of 2014, the X-ray brightness was higher, the star is brighter in X-rays than we'd ever seen it before. So it'd be very interesting to see if this continues. The X-ray minimum was reached on August 2nd, 2014, and this is consistent with this 5.5-year orbital period. The recovery of X-rays from the X-ray minimum was intermediate between the fast recovery we saw in 2009 in the previous orbit of the star and the delayed recoveries which we'd seen earlier with RXTE. And so why is this important? Well, this is important because for stars, mass determines their destiny. But for massive stars, mass loss determines their destiny. And the X-ray emission is dependent upon how the stars are losing mass and what the instantaneous state of that mass loss is. So by looking at these X-ray variations, we can tell something very important about how the stars are changing in their mass loss properties. And this is either the mass loss from Eta Car, its companion, or perhaps even both. So thank you, and I'd like to turn it over now to Mairan Teodoro, who will tell you about the results of an extensive campaign of ground-based observations.
Thank you, Mike. First of all, thank you all for being here, and I'd like to ask your patience because this is my very first talk in English. So I'm going to talk a little bit about the changes that we had monitored in. Let me just. I can see it. That we have monitored over the last 22 years. We're using a lot of data from all of these people spread all around the world. Here you can see the distribution of observatories, and some of them are amateurs, and some of them are professional. Like I don't see the cursor right there. So in South America, most of all of the 3 stars that are shown there, they're professional observatories. And from Australia and New Zealand, we have only 1 professional observatory, and all of the rest are from amateurs. So we have a very good contribution from the amateurs. And we chose the helium-2 4686 line. This is a spectral feature that it was discovered 10 years ago. In 2003, I think, we had the first measurements of this optical region, and we first detect this transition back in 2003, and the publication with the results came only in 2004. So for 2003, which was the year of one of the first monitored spectroscopic event, we couldn't have a time sampling of the observations as good as we have for the past 2 cycles. So the good thing about this line is that you can see here, that's the optical spectrum. I can't use the cursor. You can't see anything there. Okay, so that's the optical spectrum, which arises from the primaries wind. The central picture, it's an illustration from Tom's model. This is a simulation, 3-dimensional hydrodynamical simulation, that shows the primary and the secondary stars, the primary and the secondary stars at a pastrum. So the secondary star is the yellow dot within the blue region right there, and most of the yellowish and orange regions are from it's the primaries wind, and Mike just talked about the X-ray variability, which is caused most of the X-ray variability is caused due to the secondary wind colliding with the primaries wind. So most of the X-ray spectrum is produced in the post-shocked secondary wind. But the optical helium-2 line, it's not produced that. Although both of them are produced very close to the wind-wind collision region, one is produced, the X-ray is produced on the secondary side, and the helium-2 on the optical is produced on the primary side. So both of them requires a lot of, the emission of the X-rays and that line requires a lot of energy to be emitted, but they track very different environments. So we used we monitored the helium-2 line over the past 2 cycles, and I'm going to show you that we don't see much of a change. I mean, it's not significant change that we see in the emission of that line. Although we have a lot of variability in the X-rays, we don't see the same in the optical region, especially in this spectral feature. So the data. This is the measurement of that blue region, shaded region that I just showed you. And I'm showing here the strength of the emission. So this is kind of showing how strong the emission is when we go across periastrum. So this is the first data set that we have. We have more data spread all over the past years, but this is the first data set that we have across periastrum with a time sampling that is fair enough to compare with the recent observations. So you have here in the horizontal axis time frame of 11 months. So we have, I would like to show the cursor, but you have all the dots mark the strength of the line. So we have, as we grow across periastrum, we have an increase in the strength, and then we have a very rapidly decrease. And then we have another increase in the strength. But with this kind of data set, we can't tell much about the shape of this variability. So since that was the first data set, and it was observed in 2003, the publication of the discovery of this line was done in 2004, and then we had the possibilities to carry out a more detailed monitoring. So this is for 2009. You can see the year on the top axis, and this is technical. This is the bottom axis is only the days regarding specific date. So this is for 2009, and we had a lot of a much more finer time sampling, and when we look very carefully and within the details of this variability, we can see that there is much more to explore than just meet the eye. So we have at least 3 peaks in the emission of the helium-2. We see a first peak arising, and then it goes down, and then it rises again, and then it's all the way down to completely eliminates the line from the spectrum. And then it rises again, and then it fades again. And it spends, this line spends most of the orbital cycle, orbital period, at a very low level. If you take a spectrum of Eta Car during apastron, you will see almost nothing of the line. Although you see a little bump there, but there's a little production of this optical line during apastron. So that's why I'm showing you only the 1 year around periastron. So this was the first international campaign, which brought together astronomers from different professional observatories, and we had a contribution from at least 5 or 6 different observatories. And this was for the 2014 international campaign. This was the second international campaign, and you can see that the name of the observatories are shown on the top of the plot, and we have pretty much much more information this time than we had in the past 20 years. So now we see a beautiful rise of the strength, and then you can't see very clearly, but there's a dip, and then you have the major peak, and then it goes all the way down, and then it rises again, and then it goes back to 0. So since we have much more information, temporal information of on the variability of this line now, we decided to compare the 2014 and the 2009 light curves, which are shown here as the black is for the current event, 2014, and the red is for 2009. And this is focused on the periastron passage. So I'm not showing the rise of the intensity because we don't have that many observations for 2009. So our question is, since this line tracks the behavior of the primaries wind, can we see any changes on that region? So we ran statistical analysis on this, and as you can see, the curves, the black dots and the red dots, they are pretty much close to each other. So there has been no changes, I mean significant changes in the past 5.5 years. And just to illustrate how the curve would like with an increase in the intensity of 20%, this is what it will look like. And if that would haven't happened, we would have detected it as a significant change. So although the data analysis and the reduction of the data is very complex, the results are very simple. I mean, there has been no significant changes in the primary side over the past 5.5 years. So if there has been some changes, it's not larger than 20 or 30%, of course, in the primaries wind. So although we didn't detect any changes on the primary side over the 5.5 years, we do not discard changes on longer periods of time. I mean, for the next event, which is predicted to occur in 2020, we would have the chance to compare the changes, to measure the changes in the light curve for 3 cycles. And that would give us some insights on the changes on longer term, over longer periods of time. So we do not discard that there has been some changes in this emission, but over 5.5 years, we don't have significant changes on the emission. So that's it. I'm going to pass the presentation to my colleague Tom. He's going to be talking about his beautiful modeling. And that's it. Thank you.
Just gonna set this here. Good morning. So my name is Tom Madura, and I am a NASA postdoctoral program research fellow at NASA Goddard Space Flight Center. And I'm here to talk to you about how we are using 3D supercomputer simulations and 3D printing in order to better understand what is actually happening in the central interacting binary within Eta Carinae. So I'm actually a theorist, as opposed to most of the panel here who are observational astronomers. But what we do is we actually use the detailed observations from Eta Car to build a 3D supercomputer simulation of the central interacting binary. And this is what I'm showing here. And what we do is we use the simulation to try and better understand what is happening in Eta Carinae in the present. And then we get future observations and feed them back into the model. And we try to make predictions of what is going to happen and try to understand some really complicated and interesting physics that are happening not only in Eta Carinae, but are applicable to massive stars and binaries in general. So what you're seeing here is on the left is a density plot, and on the right is the temperature. And you can see that, the cursor doesn't want to, oh, there it is. So here is the more luminous, massive primary star, and here is the secondary star. And as has been discussed by Mike and Mairan, what happens is the low density, high velocity wind of the secondary star collides with the dense, slower moving wind from the primary, and at that interface, all of the energy has to go somewhere, and it goes into heat, and this is the gas that is responsible for the X-ray emission, and this is an animation. So for most of the orbit, when the stars are far apart, not much happens, and you get a very nice, symmetric, what's called wind-wind collision region. But because of the very high eccentricity of the system, when the stars start getting closer and closer and closer to each other, their speeds go faster and faster and faster, and then at periasteron, you get this very beautiful Archimedean-like spiral structure. And every 5.5 years, the binary system is doing this. And if you pay close attention, you'll see, I'll let the movie play again, you'll see that on the temperature plot, what happens is when it goes through that periasteron process, we actually get some really complicated and interesting shock physics going on. And the hot gas responsible for the X-ray emission actually vanishes. And we think that this helps to partially explain that, that long, deep minimum that occurs in the X-ray light curve that Mike showed. So now you can see where the part of the hot gas has disappeared. But one of the things you can imagine is that these are just slices looking down on the stars, looking down on the orbital plane as the stars go around. We don't have a very good understanding of what the actual full three-dimensional structure of this wind-wind collision looks like and what it means, and not only for this system, but in terms of interpreting the observations. So what we've done is we have found a way to, using a commercial 3D printer, in this case this is a MakerBot Replicator 2X, we have found a way to 3D print the output from our supercomputer simulations of Eta Car. And as far as we are aware, these are the world's first 3D prints of a supercomputer simulation of a complex astrophysical system. So what I'm going to show here is this model right here. This is one of the most interesting results, one of the most interesting phases. So this is at a time of 3 months after periastron passage. So periastron is when the two stars are closest to each other. And what you can see in the left is this is the wind-wind collision region. So the model is actually in two pieces. The top part represents just the high-density part of the wind-wind collision. And the bottom part here actually represents that very dense primary wind that's being created by the primary star. And then the model is actually separable. And if you look, you can actually see the wind cavity that is carved by the low density wind of the secondary star within the dense wind of the primary. And then here are the two little stars. So here's the more massive primary star, and then here's the companion star. But what was really amazing was, as a result of doing this 3D printing work, we actually discovered these finger-like protrusions that extend radially out of the spiral wind-wind collision region, and these are features that we didn't even know really existed. And so, only as a result of doing this intricate 3D modeling and 3D printing did we discover these. And we think that these are real physical features that arise due to physical instabilities, where you have this really fast wind from the secondary colliding with what's essentially a wall of gas, and then you can get all kinds of different turbulence. An analogy would be something almost like vinegar and water, the different types of instabilities that occur. This is a very nice 3D rendering. So this is actually from the 3D supercomputer simulation, and we gave it to our conceptual image lab at Goddard. Whoops. And this shows you a very nice zoom of the 3D wind-wind collision region, and it gives you a very nice perspective of these protruding fingers that jut out from the colliding wind region. And we've actually discovered a number of very interesting features. So for instance, this hole that is visible here is actually another real physical feature, and it's a result of the fact that during this highly eccentric orbit, the two winds are no longer able to collide. And so you actually just don't have a wind-wind collision region there anymore. And just to give you an idea of how complicated this is from the exact same simulation, except this is just showing you what the structure looks like at apastron when the two stars are farthest apart and the orbital motion of the stars is slowest. And you see that you have this very nice symmetric conical cavity. It looks almost like a radar dish. So what we've done is, as a test, we just did 3 what we thought were the most interesting phases. You can see in the top row is apastron when the stars are farthest apart. Middle row is periastron when the stars are closest together. And then the other view, which is the other phase, is the spiral phase 3 months after periastron. And at this scale, 1 inch, to give you an idea of the sizes that we're talking about, 1 inch is equal to about 35.5 astronomical units, which is 3.3 billion miles. And we've also constructed the models such that you'll notice that they have a flat bottom and there's a sharp edge here. This isn't just so that they sit nicely. we've actually 3D printed these so that if a person holds it like this, and you look directly straight like this is the view of the system from Earth. So you can set it on a tabletop, and you have an idea of exactly how we are viewing the system. And all three of these are like that. And so that's the first column there. So to conclude, the 3D printed models provide an innovative way to visualize, interact with, and communicate the results of very complex 3D simulations. One particular application would be teaching astronomy to, say, the blind or visually impaired. They don't, unfortunately, have the ability to view beautiful 3D computer simulations, but something like this provides them the ability to have a tactile representation of a supercomputer simulation. It's also a great way to communicate science results, complicated science results to non-experts and the general public. We are going to make the 3D print files for all of these models will be put on a website hosted by NASA Goddard, and they will be made freely available to the public. So anyone who has access to a 3D printer will be able to download the models and 3D print them themselves. As I've shown you, this allows us to identify previously unknown structures, and it helps us immensely in interpreting and understanding the observational data. And at this moment, I would like to pass the talk over to my colleague Ted Gull, who will now talk about some very interesting colliding wind features that have been discovered with the Hubble Space Telescope. Thank you.
While I'm setting up, I would just like to point out that Wolfgang Steffen is here in the audience, and he was very instrumental in helping us put together a 3D model of the homunculus, which probably on this scale would be about a 6-story structure in which Eta Carinae is buried in the very center. You may want to talk with Wolfgang after the session here, but we, as a team, have been working with him on this. I'm going to talk to you about some observations that we've done with the Hubble Space Telescope. And these are the observations that really started me down the path of saying, hey, we need a 3D model of the interacting winds, and teaming up with Mike Corcoran and Mairan Teodoro and many other people around the community to study this interesting object called Eta Carinae. And it really has been a widespread team activity. The study I'm going to talk about is using the Space Telescope imaging spectrograph coupled with Hubble. And it's a study that has been extended across almost 6 years now. During these 6 years, we've seen some very obvious spatial changes that I'll try and impart to you, but I'm only going to show you a thin slice of the huge data set we have, and it's only a thin slice of one line. The first observations that we did with this was a test observation showing that the Space Telescope imaging spectrograph was back in operation after the servicing mission 4, when the astronauts went out, and after a very lengthy EVA managed to repair the STIS and get it operational again. Let's go back to this slide that Mairan Teodoro was showing you a while ago. Here's the helium-2 line that he was discussing, and that is the line that is coming from the primary wind side of the shock region. But if you look at this spectrum, you can see there's a lot of other complex lines here. And anybody that works with Eta Carinae says, oh, it's a mess. But here's another line of great interest to us. It's a forbidden iron 3 line. And if you look at it very carefully, you see that at apastron, it's very, very strong. And then it decreases during periastron. But look at it a little more closely, and you see that there's a shoulder, a blue shifted shoulder here on the side of the line. And also there's a red shifted shoulder, but it's of less interest, at least in what I'm going to present today. Well, from the ground, these two observations were taken 2 3/4 years apart, periastron, apastron. We see variations within what's ever happening within the seeing disk of 2 arc seconds approximately. But we know that the X-ray and helium emission is coming from regions that are far, far smaller than that, 100 to 1,000 times smaller. You'd like to know, well, what's going on in between the seeing disk of 2 arc seconds and, say, the 10 to 100 milliarc seconds region that everything's happening down there that Tom is modeling and we're observing with X-rays, et cetera. Well, you can't quite can't resolve that from the ground, but you almost can. And in fact, it turns out you can do it with Hubble and the STIS. Now, here's one example of a spectrum that we took with a 2 arcsecond long slit, 1/10 of an arcsecond wide. And what we're seeing here is a part of one line profile of that iron 3 emission. And if you look at this very carefully, you see, well, it's only between 0 and blue shifted 450 kilometers per second. That is 1,000,000 miles per hour, if you want to put it into context there. Excuse me, I've slipped it. But what you see are all these blobs and streaks of structure that have come out of forbidden iron 3 emission. Now, the iron 3 is coming from a cooler gas, probably about 10 to 20,000 degrees Kelvin. By the way, that's about the brightness or the temperature of the surface of our sun. But if you could picture this, it's extended over a region that is far larger than our solar system. So this is a very large, diffuse, clumpy gas that's extending over huge distances around Eta Carinae. So this is just one slice. Now, if you can do this well, rejecting Eta Carinae's emission 3/10 of an arcsecond away, then why don't we put together a map? And that's what we proceeded to do. Here you see a 2 arcsecond by 2 arcsecond box. We took the Hubble STIS with that 2 arcsecond long slit, 1/10 of an arcsecond wide, and shifted it every half slit distance. So there's 41 slit observations that we do every time we observe Eta Carinae. And you might say, well, that takes forever. One orbit. It takes one orbit, 96 minutes to do it, if you time it carefully, of course. And what you see is a slice coming out of this of structure that is the blue shifted, the gas that's approaching toward us. It's a narrow slice. It's only 40 kilometers per second wide at 140 kilometers per second blue shifted toward us. In other words, 300,000 miles per hour. So what you're seeing here is structure that came out of Eta Carinae over the past several different cycles. And some of these structures came out as long ago as 16 and a half years ago, 3 cycles ago. So let me go to the next slide here. And you see Tom's models here at the bottom. This is Apastron when the stars are widely separated, 30 times our astronomical distance from the Earth to the Sun. And the ultraviolet radiation can escape from the system. So that ultraviolet radiation escapes and it photoexcites all of this gas up here. You see it in iron 3. But when the system wraps around, that very rapid passage during periastron, the primary wind gets in the way and it absorbs all of the far ultraviolet radiation. And so as a result, the gas just simply relaxes and you no longer see it in this forbidden iron 3 emission. I will say as a side, it goes from iron 3 to iron 2, and we see a yin-yang type effect going on here. But this really is showing that the gas is being photoexcited directly by the far ultraviolet radiation, and it turns on and it turns off with time. So this is really an exciting thing because we see at astrophysical laboratory the light source is exciting it, the material was just changing with time, and we can see the changes. Now I showed you what Apastron and periastron did, but actually over the past 5.5 years, we have periodically gone with the STIS instrument and observed Eta Carinae now 11 times. There's one image that's reproduced there twice on it. And if you look at this bottom row down here, this was the first observation done in 2009, and you can see that the structure is rather diffuse, and then it develops almost a crab-like structure in this velocity slice that I'm showing here. And you can see that there's 2 claws that seem to be appearing here, and they expand outward with time. And then as we go along, and this is about a 5.5 period, it's not sampled uniformly. We do it about once every year for several periods, but as we get close to periastron, we're sampling more rapidly because we wanted to see critical changes that are predicted from the X-rays, the helium data, and Tom's models. So we're all working this together to see what's happening with it. And what happens, of course, is you see that the iron 3 disappears, and for several months it's gone, And as of December 17th, it's coming back. So you see the fading as the UV radiation disappears, and then it comes back here. Now let's go up to this video here that I'm showing of, and again, it's not linear with time, but look at this claw here. You can see it's moving outward with time. And if you take the differences between frames that are a year apart, it's about 10% variation. That claw came out 10, 11 years ago and is really due to 2 cycles previously. And you can look at this bottom claw there, it's doing the same thing. So here we're seeing structures moving out with time, we're seeing changes in illumination, and indeed if we look further at other wavelengths, we actually see a lighthouse effect where you can see where the far ultraviolet radiation is hitting different parts of this cloud structure to illuminate it and then moving on, just like a lighthouse would be light would be doing from a lighthouse. So there's some really exciting structures here. And as we look at each of the individual things here, we're going to get a clear idea of what the spatial structure is of the winds themselves. Already I can tell you, like what Mairan was saying, is there's not much change in the primary wind, but we're seeing obviously other changes. We've got to do much more work with the models, work things through with time here, and I think we'll have a much clearer idea of what Eta Carinae itself is doing, but also how radiative winds are doing in systems like this. So in summary, the Hubble STIS is really uniquely resolving what I would call fossil winds here. And I'd probably drop this, but effectively what I've been doing over the past 5 years is astronomical archaeology. I've really been excavating the structures that are left over from previous cycles and trying to project back to what the system is doing currently. Parts of these fossil winds glow because of the far ultraviolet radiation from the secondary star that glows that illuminates for most of the 5.5 year period. But then across the periastron time, the light is captured and stopped by the primary winds, and the glow fades. It actually goes from Mairan 3 to Mairan 2. And then we have a record now of what's changing over a 5.5 period. And hopefully we can continue doing this for longer periods with Hubble, but it really is an exciting thing. Now, if we think a little bit into the future, if we build bigger telescopes, possibly in space or that, a factor of 10, if you think about that, which is a huge telescope, admittedly, we could then start resolving the structures that Tom is showing here. And that really gets exciting. Okay? Thank you.
As usual, we now open the floor to questions. Rick Feinberg is holding the microphone, and we welcome questions also from the web. Please wait for the microphone and identify yourself and your affiliation when you ask a question. Goddard? I think it is.
It is. Govert Schilling, freelance from the Netherlands. A question that maybe everybody is thinking about: when will this stellar monster explode? And do any of your observations give a better handle on that expectation?
Well, we don't really know when it's going to explode. It may have exploded already, but we doubt that. But our observations tell us about the mass loss. So if there's a tremendous change of course, what determines the eventual fate of the star is what's going on deep in the core. So we're looking at very much surface phenomena. But having said that, the surface phenomena should be indicative of what's also responds to what's going on in the core. So if there are tremendous changes in the mass loss rate, for example, that we could monitor with our observations, that may be indicative that something dramatic is happening deep within the star. There are observations of recent supernova like 2009 IP, which seems to have undergone sort of great eruption-like events right before it finally exploded. So there may be some connection between these large events and what's going on deep within.
Could I answer that with two responses? One is that really Eta Carinae seems to be in a stage where a lot of nitrogen is being produced, and we don't really expect it to become a supernova. However, we can always be fooled. But the tongue-in-cheek response to this is, well, the most unstable part of the orbit is when the two stars are closest together. So if you want to take 5.54 years and multiply it by n, you guess what n is, and it could be 100,000, but sometime in the next few 100,000 years, it's going to go.
And if
On the
you
other hand, it's a wonderful laboratory.
and if you look at that modulo 4 as well, you can see which meetings we're going to be talking about the explosion at.
In the 1980s, as Ted was just saying, nitrogen was discovered. It was very enhanced in Eta Carinae. And they had put out a press release on this, and that got to the White House. And Ronald Reagan said, if Congress doesn't pass this bill soon, Eta Carinae is going to pop off as a supernova.
And that comment was coming from Sally Heap, who's one of the principal investigators on an earlier generation of Hubble's instruments. So she knows from what she's talking about. Any other questions in the room?
Other questions? Yeah, right there.
Hi, I'm Nadia Drake for National Geographic. Can you talk a little bit more about those bright X-rays in 2014 and what you think might be going on there? Because the peak is quite a bit taller than the other years.
Yes, that's correct. Part of that is a natural effect due to the expansion of the homunculus. So there's a little bit less absorption that's absorbing the softer X-rays. But that doesn't really explain the change in the harder X-rays that we're seeing. The only thing that can really be related to is a change in the density of the wind of the companion star. Because when we see these hard X-rays, they're basically the wind from the companion star that's totally decelerated against the big wall of the primary star's wind.
Any other questions from the audience right now? By the way, these bright lights make it hard to see you, so wave your hands violently. If you, any from the web?
There's a question from Kelly Beatty from Sky and Telescope for anyone on the panel. She'd like to know more about the characteristics of Eta Car's secondary. Is it also massive and unstable?
I'll take that one. So I think part of the problem with that is we actually still don't know what the secondary star is, and that's one of the reasons why we're doing all of this work. Part of the problem is Eta Car itself is so luminous that we can't really clearly see the secondary star. And if we want to relate this back to the Great Eruption, everyone thinks that it was the more massive star who had the eruption that threw off the Homunculus Nebula. But to be honest, we actually don't even know which star had the eruption. So as far as how stable Eta Car B is, that's also still a bit of a mystery. But based on what we know from the observations from the X-rays, the helium-2, the HST, we believe that the companion star is, I guess, the more stable star in the system, and that it's the more luminous primary that is the more unstable of the two.
And then a follow-up question for the same. How might the secondary have influenced the eruption in 1841? Also, since Eta Car lost so much mass, did that mass loss influence the secondary's orbit?
It's a good question that we're trying to answer, but I would ask people to look at this homunculus model, and there's some really weird structures sticking out of there that we think are due to the 1840s eruption. It's not just a bipole, but a bipolar structure. There's some wings sticking out, and it's obviously a clue. I would hand it to a theorist and have them try to figure out just what's going on. I mean, we knew it's been bipolar for many years, but what are these wings? There's something here that we need to understand, and it's going to challenge some theorists to get through this. Was it a stellar merger? Was it the spin of the star that threw material out? We don't know.
So I will comment from the theoretical side. One of the things that's very interesting about the binary and its relation to the Homunculus Nebula is, well, let's use one of these. That's what they're for. That's fine. So there's the plane that the two stars orbit in, and then there's what's called the orbital axis, which comes perpendicular out of this plane. And actually, one of the main results of my PhD work was showing, by modeling observations that were done taken by Ted with the Hubble Space Telescope, is that the orbital plane lies in the equatorial region of this of the homunculus. So this perpendicular axis, perpendicular to the orbital plane, is actually aligned almost perfectly with the symmetry axis of the homunculus. The other thing that is very interesting is that the orientation of this cavity on the sky, the way that this cavity opens, is it actually opens up in the exact same direction as these two protrusions that jut out of the homunculus nebula. And the angular separation between these two protrusions is also almost the exact same as the angle of this cavity. So there does seem to be a lot of evidence that, at least indirect evidence, that binarity played some role in the formation of the homunculus. Now, whether it was the secondary itself that came in and there was a stellar collision, or whether it was a triple system and two stars merged and now we're left, two of the stars merged and now we're left with just a binary, that's something that future theoretical modeling will have to determine.
And Kelly has a third question for Teodoro. Because the X-ray emission varies from periastron to periastron, are you surprised that the primary's wind did not vary much?
Yeah, that was one of the exciting results, that we would expect that if the most unstable star is the primary one, the primary star, so why is the emission that comes from that the primary side is so stable over the 5.5 years? So yeah, it seems that it's a little bit surprising, but it tells something about what's going on the system. So apparently, as Mike was saying, the secondary star is the wind of the secondary star is more unstable than the wind of the primary star. So all of the changes in the X-rays could be a result of the evaporating material in the line of sight and some intrinsic changes in the secondary wind. So yeah, it's apparent. It looks like something contradictory, but it's not. The helium-2 comes from the primary, and the over 5.5 years, it has been very stable, and the secondary wind produces the X-rays. So although they come from the same region, almost the same region, they tell us different stories. So from that point of view, they are completely different.
Could I add something to that comment? And Mairan is sort of the leader of a group of unsung heroes, being professional and especially amateur astronomers around the southern hemisphere, who literally, with their amateur telescopes and spectrographs, were within hours sending us data on the helium profiles and such. And I think it's a real tribute to him and his leadership, and to he and Augusto Dominelli in bringing this coordination together. We have well over, 250 observations monitoring the helium variation across the periaster in this event. And most of it was done by amateur astronomers in the southern hemisphere. And I really thank them.
Yeah, me too. Actually, it was almost 400 observations.
Okay.
Other questions from the web? Or from the audience?
I actually have a couple. Yeah, this is Rick Feinberg, AAS press officer. I just wanted to get a clarification on scale. So Ted mentioned that the homunculus is, if the homunculus were at the same scale as the 3D printed models here, that it would be, very large, 6 stories or something. Where, relative to these models, where is this crab feature? I got the sense that it was, it's well outside, but not dramatically outside the scale of these.
Tom has some wonderful models that actually show 2 cycles of the wind structure. We didn't have time to show them today, but they are at the scale of the Hubble images, and we will be producing, or we will be working together showing the observational slices and the theoretical slices to compare those structures. Right.
Are they?
They're what?
I mean,
10
they're,
times?
Yeah, so the simple answer is it's about 10 times bigger than this.
so it's within the scale of the room, basically.
Yeah, yeah.
But
So,
not,
yeah.
but not
Almost
hugely
exactly,
outside.
almost exactly 10 times this.
Okay.
And how does that relate to our
Yeah, that was my other question is, it looked like the maximum separation of the stars was a few tens of AU, which would mean that they're comparable
Right.
to the separation of the
So-
Sun to Neptune. But how close do they get?
They get about almost the separation between the sun and Mars.
Mars.
And these are stars that are millions of times more luminous than the Sun's, just to, so that,
Right.
I mean,
They're. I mean, it's very interesting because the star is the primary star is so, its wind is so dense that it's almost the secondary star is almost orbiting inside of the other star. It's a very unusual phenomenon.
Are there radiative interactions between the surfaces of the stars?
Yes,
too?
and that's actually one of the things that we think. This was also some work done by a colleague of ours, also at Goddard, Christopher Russell, and we've been finding that what happens is so you can imagine that these stars are so bright that the radiation from the star is actually pushing the atoms in the atmosphere and blowing them out into space. But if you have 2 stars that are really close together, now you have not just the radiation from the one star blowing this way, you have radiation from this star pushing in the opposite direction. And because the one star is so much brighter than the other, we think that the radiation from the more luminous star actually slows down or inhibits the wind from the companion star. And what happens is the wind speed gets cut almost in half. It goes from it gets cut in half, and when that happens, the winds don't collide as fast, and you don't get as high a temperature gas, and so that helps explain why the X-rays disappear.
Pardon? Yes. Okay. There is one more question from the web.
Yes, there's one more follow-up question from Kelly. She would like to know the orientation of the secondary's orbital plane with respect to our line of sight.
Yeah, I guess I'd be the best for that. So it's like this. So the binary system is inclined away from us by about 45 degrees, and then our line of sight is prograde of what's called the semi-major axis by roughly 10 degrees, and then again the orbital axis is almost lined up perfectly with the symmetry axis of the homunculus on the sky. So, and think of it as inclined away from us by 45 degrees, and then just rotate it to line up with the homunculus.
Tell him he has to make a 3D model, and then he can understand it.
Just print it out.
Yes, print it out, and it'll be much easier.
We'll wrap that up. If you have any other questions, please come up and ask them. I would like to announce 2 things before you leave. First of all, there is at 2:15, the second of our press conferences of today. This is a new feature of our meetings. I think we had it at the last meeting as well. It's a seminar for science writers, not necessarily breaking news, but background information, and this is on the Hubble's achievements. So this is going to have a very colorful and informative session on Hubble's major accomplishments and Hubble's highlights over the last 25 years. And my memory fades back then. And secondly, if you have some energy after that, tonight is the Wednesday night of our meeting, and it's traditional to have a party. organized by Gina Brissenden and company. It is at night hours, and if you want details on it, there are little cards like this in the press room, or just buttonhole Gina. And we'll see you at 2:15. Thank you very much. And thanks to all our speakers.